and have played about with Lego blocks, as you can see here at some point in your life. And with this Lego blocks, you can create many complicated, very fascinating kind of structures like I'm showing here. Or if you're a Star Wars enthusiast like I am, you can even make even more fanciful structures like the Millennium Falcon in here using the same Lego blocks, the same building blocks that I showed in the in this picture. You might also remember about playing Tetris, where again the game is all about fitting all these different blocks of different shapes into making a uniform structure. So in this lab, what we do is that we play basically same sort of games, but instead of using Lego or the Tetris blocks, we use atoms. And with these atoms, we create designer materials one atomic layer at a time. And the way we do it is by using mostly a technique called a molecular beam epitaxy. And then today in the Chai and Y session, we are going to tell you about how we go about doing it. So, as a very crude first order approximation, you can think of this as an atomic spray painting. So I'm sure, all of you have done some spray painting probably during your school or college days, where, you remember you have these sort of a spray cans, and with this you can create all your patterns. Now just imagine that you have these spray cans, which instead of spraying out different colors, can now spray atoms, as I'm showing you here. And what we do in this technique is that we start with a well-ordered crystalline surface. So this is a surface where, the atoms are arranged in a periodic manner. And then imagine that with these spray cans, you are just basically raining down atoms, and you're creating these materials in a bottoms-up manner by the process which is known as epitaxy. And this is basically a juxtaposition of two words, which is epi, that is the top layer. This is the top layer that is being formed, which is now taking the shape of the underlying layer, which is the taxi part. And this allows us to grow these sort of materials in a bottoms-up manner. Now, you might wonder, like, what can we do with these things? So we can now create, with this technique, materials that have no bulk analog, or to say that you cannot really get these sort of materials out in the nature. Okay. For example, here in this picture, as you see, we have a material of few atomic layers of one kind of material. Then we have grown another material on top of this, and you can keep going on. And this is called a superlattice structure. So this sort of structure, which you can create because we are creating this materials one atomic layer at a time, you cannot get this in the nature. On the other hand, you can also create, for example, this sort of a heterostructure. You can see that there is one compound here, which is a gallium antimony, which is a semiconductor. On top of it, we have grown a material which is ytterbium diantimnine, which is a superconductor. So now you have a kind of a hybrid structure, which is superconductor on one side and semiconductor on the other side. So this again, you can't get naturally, out there. And these sort of materials can give rise to new sort of properties that we might be interested in. And this is what we try to do in this in our group. So, traditionally, the way you might be familiar of doing science or, in material science is that you get some materials and you try to characterize it, you try to understand the properties, and you try to figure out whether this can be useful for some, applications that you might care about. Now, in this lab, what we are trying to do is to invert the question. Okay, so let's do it the other way around, in the sense that, let's say you want a particular kind of a property. Now, you may ask the question, can we now design a material? Let's say we don't get it in nature, which serves your purpose. Can we now design a material which will have exactly the same sort of properties that we are interested in? And the answer is yes, if you have the ability to create these materials one atomic layer at a time, because we are growing this material in a bottoms-up manner. And in the process, we can have access to various tuning parameters. For example, here I'm showing this proximity effect. is the same example as I gave earlier, where you have material with one property in close proximity with a material with another property, and this gives rise to a new emergent property which is different from either of the individual properties. Similarly, you can, when you're raining down atoms, you can use a template where the atoms, that starting template is one, where your atoms are a little bit more separated than the one layer that you're growing in a bulk form. And what will happen is that the atoms will now take the shape of the underlying layer, so they will be a little bit stretched. So you can basically introduce some strain in the system while growing, and that can give rise to new properties. So in the end, our end goal is to create engineered material which has a tailored property on demand. Now, you might wonder that, okay, this is all very good. It might sound cool, but I mean, why do we really care about it? I mean, why should we care? And the answer to that is because this ability of ours to create materials in one atomic layer at a time has had a huge impact both in advancing our modern science and also technology. So here I'm just giving you one example in terms of the advancement in science. So what happened in the 1980s is that people could create very pristine semiconductor heterostructures, and that took a long time actually. So in the bulk, it was, if you look at what is plotted here is electron mobility, in the sense that given some electric field, how fast can the electrons move? And the faster they move, it gives you a measure of how clean the system is. And over the years, this number has gone up so much so that now you can have mobility of the order of 36 million centimeter square per volt second. And this is basically the most pristine material that you can find in today's world. And why do we care about doing this? Because when you have such a pristine material, you get new kind of physics that emerge. And that is what is shown here, that if you look at the Hall effect, when you put some current in presence of a magnetic field, you have a transverse voltage. And typically you expect this line to be a straight line. But here you see there are some plateaus. And what that indicates is that this is an emergence of a new sort of ground state, which is known as a fractional quantum Hall state. And this has an entirely new kind of physics where you have a fractionally charged quasi-particles. So, electron has one electron charge, but this quasi-particles has not an integer, but a fraction of charge. And this was duly given a Nobel Prize in 1998 because it's altogether a new state of matter that people found in these sort of very pristine material systems. Now, in terms of the technology, you might have heard of this quantum cascade laser. So where, it's okay if you even have not heard about it, but, these are the kind of lasers which is easily tunable, and it is you can create a very high power laser out of these kinds of lasers, and it has a lot of applications. For example, chemical imaging, remote sensing, and also in the many military applications. For example, they are used to confound heat-seeking missiles. Like if you have a heat-seeking missiles, they generally track the source of heat, so it tracks some IR radiation. And now, if you have these sort of lasers, you can actually create alternate sources from these lasers so as to confound your missile so that it misses your target. Okay. Now, if you look at one such laser, and if you zoom in and in and in, at the heart of it is, this kind of a layered material. And this ability to create this layered material is what makes this kind of technology possible. So just very quickly, so you have basically created a semiconductor with a smaller gap, and you have sandwiched it with a material of a larger gap, giving rise to something called this quantum well. And what's happening here is that the electron is hopping from the higher level to the lower level, emitting a photon. But because this well is narrow enough that the electron can tunnel to the next well and again emit another photon, and so on and so forth. And this is the cascading effect that is being used to generate very high power lasers. Similarly, just quickly, another application, if you have heard about James Webb Space Telescope, and actually any space telescopes out there, or in the space missions that is carried out by NASA or even ISRO, you see all these very fantastic images from the outer space. What makes that possible is that they have these cameras that can work in very low light condition. So they are basically sensing this infrared photons. And if you look at the heart of one such camera, which is here, which I'm showing you here, you have again these sort of heterostructures that one needs to build to be able to create these sort of a technology. And you can also create different kinds of solar cell. Actually, with these sort of a heterostructuring, you can create the most efficient solar cell that is known in today's world. And this was also appreciated and given a Nobel Prize in 2000. So now that hopefully I have given you some motivation that why we should care about this ability to grow and create designer materials, let's ask the final question, that how you actually go about doing it. And today's Chai and Why is going to be about exactly that. So let's dive in and look into a molecular beam epitaxy system. And here I'm just showing you a schematic, but the actual equipment looks exactly like this. So we can, yeah. So, all right. So you can see this is the equipment that I had shown you in a schematic form that makes all this happen. And to let you walk you through how exactly we go about doing this. So here is Rudra and Shankhadev. They are going to show you how exactly they grow this one example that I showed, a semiconductor and superconductor hybrid using this molecular beam epitaxy. So Rudra.
So hello everyone. So I'm Rudra and I'm going to show you how we okay. Hello everyone. I'm Rudra and I'm going to show you how you grow this kind of material on top thin films on top of a substrate. So this is example of one substrate. You can see this is a very shiny side which is atomically polished, and on top of it we grow our thin films. So yes, okay.
So this shiny thing is
the
substrate on which you have already grown something, or
no? This is a bare substrate.
Bare substrate.
So we put the substrate inside the molecular beam epitaxy and grow our material on top of it.
Substrate is what material?
This is a silicon 111 substrate, but there are different kind of substrates like gallium antimony or Al2O3. Depending on the film, we choose our substrate.
Okay.
So to explain more about the molecular beam epitaxy, I'll show you some slides. Okay. So as you have seen, this molecular beam epitaxy is a huge system and it has lots of different components. So
the time being very
okay. So it has lots of different systems like a fusion cell, and we have maintained ultra high vacuum. And to calibrate the flux, we use QCM, and to monitor the crystal growth, we also use electron diffraction. Now, one key concept in the growth is evaporation or sublimation. So as you all know, that water has these three general phases: liquid, solid, and gas. Now, in the so when the water converts from solid to gas, it is called sublimation, and when it converts from liquid to gas, it is evaporation. So similarly to water, these metals also can go through this transition, but for that we need very high temperatures. Now you can.
Am I right in saying that you make a gas of a metal?
Yes, correct.
Okay.
So this metals also has this. You can define the partial pressure for the metals also. So this is defined by this relation. And as you go up in temperature, you can increase the pressure. Hence, you can increase the number of atoms which is evaporating from the metal surface. So basically, in molecular epitaxy, we do that using a controlled manner, which is and to do that we use a particular cell called effusion cell. So this is the effusion cell.
So if I have to draw a similarity between water evaporation
Yes.
and the evaporation that you are trying to do for growth,
Yes.
is it like same physics principles or?
The physics principle is more or less same. Yes. So basically, we put our material inside the crucible, and there are some heaters. We heat up, and thus we can get this kind of molecular beam. And these molecular beams are aimed at the substrate. Now, Sankadev will show you where the effusion cells are in our molecular beam epitaxy.
So, hello. So this, you can see these things here. There are several you can see. So these are the effusion cells from which we actually spray the atoms. So these are the sprayers Professor Shovik talked about. And there are different elements in this. For example, we have yttrium, aluminum, gallium, different metals in different cells.
You have
So-
to separate every material you want to evaporate.
Yes, we have separate source for every material we evaporate. So
Are you able to control them independently?
So everything, so it depends on the temperature. Everything has a heater and different temperature sensors. So if you focus here, this is the power source and these are the temperature sensors we have. And obviously there are water supply also to keep them cool. And you can see here, everything has a separate shutter. These things are actually shutters. So we can actually control exactly when we want to let some atoms go and make something using the shutters. And that is why we can actually control how we can go layer by layer, atomic layer by layer materials using these shutter controls.
So you
Exactly.
say the gate.
Yes,
If when you want to evaporate some material and go to the substrate, you open the gate
yes,
and then you
exactly.
can close it.
Yes.
And
And-
how fast does it have to be? I mean, how fast does the shutter close?
So it is very fast actually. And actually the process is really slow. So it is, the atoms are coming out really slow. It is really controlled manner. So it is one of the most controlled processes we can grow a crystal. Atomic layer by layer, you can see.
So shuttle speed is not something one should worry about.
No, it is not to worry about. So I will pass on to Rudra.
So now let's understand about the another important aspect for this kind of molecular beam is the ultra high vacuum condition. So let me share some slides. Okay. So another important aspect for this to get this molecular beam is to have a ultra high vacuum environment. So for example, you have this effusion cell and you are heating this up.
Okay. Okay. So you already explained.
Yes.
Okay. Actually, just a naive question. What exactly is ultra high vacuum?
I'll explain. So so you are heating up the effusion cell. So ideally you should get this kind of beam of molecules like gallium. But in reality, in atmosphere, there are lots of these gases and they will hinder the path of this molecular beam. To get the molecular beam, we need to get rid of all the extra gases present in the atmosphere. And so do that, we pump the system to very low pressure. So the pressure is even lower than the surface of moon. This is 10 to the power minus 11 millibar. So there the mean free path is around hundreds of thousands of kilometers. So in atmosphere, the mean free path is 70 nanometer. But so your molecules that are coming from your effusion cell cannot travel beyond 70 nanometer without any collision. So effectively, if you have like some long distance, all the molecular beam will scatter out and you will not get very good control over your flux. And another important point for the ultra high vacuum to get very high purity material, because you know these gases and all other things can react to your thin films because your material amount is very small. So a very small amount of impurity is a lot for the thin films. So this that is why it is very important to maintain the ultra high vacuum. So it is not very easy to reach the ultra high vacuum because the pressure is lower than the surface of moon. So to do that, we use different kind of pumps and baking. So here you can see a scroll pump. So this pump can pump down to 10 to the power minus 2 millibar. And now you can add a turbomolecular pump, which is basically a jet engine like structure, and it has a blade and it rotates and compresses the gas and feeds it to the scroll pump. So if you add that along with the scroll pump, you can achieve around 10 to the power minus 7 millibar of pressure. Now, another problem, if you open your chamber with the atmosphere, so what will happen that all the moisture will get absorbed in the wall of the your chamber. So they comes out slowly, and that is called degassing, and that will make your pressure very bad. So to get rid of the moisture, you can bake up your system. So we bake our whole system like that to 150 degrees Celsius to get rid of the moisture. And now if you want to go further, you can use some specialized pumps like iron pumps or cryo pumps. So that can pull the pressure down to 5 into 10 to the minus 11 millibar. But one catch is that this whole process takes around 2 weeks. So ideally, if we open the chamber to atmosphere, then it will take around 2 weeks to get the pressure. But we don't do that. We don't have that much time. So to save time, we use a load lock kind of setup.
Just to give a recap.
Yeah.
So basically, at some stage, you are starting from atmospheric pressure,
Correct.
which is not just air, but also a lot of moisture,
Right.
which is perhaps your most worrisome component.
Yes.
And to get rid of moisture and all other gases, you are using different pumps.
No, we first pump down the system, but still the moisture is there in the wall.
And to get rid of the moisture, you are
We-
heating the entire chamber.
Yes. And
to
to
a
achieve
temperature which is higher than boiling
point of the water. Yes.
so that you are sure that all the moisture can basically come out of the metal chambers,
Yeah.
and then you are able to pump it out.
Yes.
And this entire thing it invariably takes minimum 2 weeks,
Yes.
provided there is no hiccup. And
Yes.
if there is a hiccup, then
It
you
will
have to
take
go back
months.
and
Start again.
start again or sort out the issue.
Right.
So it's really a long drawn process
Yes.
to make your chamber to a ready state.
Yes. So to prevent that, we use a setup called load lock setup, which separates the main chamber from the direct exposure of atmosphere, but exposes some other smaller chambers to atmosphere, which we can pump very quickly to some pressure and then transfer our samples from that. Sankodeep will explain in more
So
detail
you
about
are
this
found
transfer
the
process.
convenient way to have a higher turnaround.
Yes. So Sankodeep.
Now, as Rudra have explained, so we cannot really open this main chamber. So this is our main chamber, as you can see. This whole chamber is our main chamber. We cannot really open it to atmosphere because it will take a lot of time. Now you can see our whole chamber. If you can zoom out a bit, you see this is our whole chamber, and it is divided in some parts. So you can see this thing is called a gate valve. So this is called a gate valve. You can close it, and then this part and this part are separated. So air doesn't actually transfer between these two. And you can open it to make the chambers connected. And similarly, we have a gate valve here also. So we have divided our chamber into three main parts. So this part is the main chamber, and this part is called the buffer chamber, which is both kind of a preparation chamber and a storage chamber. And I will explain what we do here. And first of all, this is called the first entry load or FEL chamber. So this is the chamber which we open to atmosphere directly. All other chambers, no other chambers actually see the atmosphere at all. So we only open this chamber, and when we open it to atmosphere, we close this gate valve so that no high pressure goes into buffer.
So whenever you are putting in your substrate, it is put in through this chamber,
Yes, we put
And
it through
also
this chamber.
taken out.
Take
through
it
the
out
same
through the same
same
chamber. So when we put the sample in, you can see here above this is the turbo pump Rudra talked about. So this is the turbo pump, and there you can see the scroll pump, the backing pump for the turbo. So Rudra have talked about this. I will not explain it much. And you can see that this we turn on after we put the sample in. We turn on this pumps and we pump it down. Also, you can see something like a bulb is running there. So that
the red thing you mean?
Yeah, red thing.
Okay.
So that is actually called lamp heater. It heats up the substrate so that as the substrate was outside in the atmosphere, it also had absorbed water on its surface, right? So you want to get rid of those and all the gases that were absorbed on it. So that is why we heat it up in this chamber. And within a few hours, the pressure goes down to 10 to the power minus 8 level. As you can see, right now, the pressure, you can see here, this is our FEL chamber. This is our FEL chamber, and the pressure is 2.5 times 10 to the power minus 8 millibar, which is a really good pressure, but it is very easy to reach. Within hours, we can reach at this pressure from atmospheric pressure. Now, you can see, after this is done, after the pressure is low and the degassing is done, so the desorbing of water is called degassing of the substrate. We can transfer it from this FEL chamber to this buffer chamber. So you can see. Now, one problem is how do we transfer? So I am going to show you how we transfer. We cannot really put something from outside, right? Because that is
the hand and take it.
Hand and take it. So we have magnetically coupled thing. It is really clever. So you can see this. This is a strong magnet and it is coupled to an arm which is inside this tube. So there is no real like mechanical connection. There is just a magnetic connection. And if I move it, you can see the arm will move and a cradle will come up. You can focus here.
Can you just take it up and down?
Yes, you can see it is coming up.
Yeah.
And going down.
So this is basically a non-contact way of controllably moving the things.
Exactly. So it is a non-contact way of moving the things. So now I will show you how we do it. So first of all, we have to open the gate valve here. The gate valve was closed, and now we have opened. We will open the gate valve. You can show maybe.
I will open the gate valve to speed up the process.
Yeah.
So now both the chambers are connected to each other. So you can see the pressure will also go up.
Yeah. So now the chambers are connected together as I said. So now what I will do is I will transfer this top cradle to the buffer chamber.
Okay. So the metallic thing that we are seeing here, that's the cradle.
That is called the
that
cradle.
You plan to send it somewhat down.
Yes.
Okay, and that's where you keep the substrate.
Yeah, the substrate is the plate you can see already.
Yes, the topmost dark color.
Plate.
That's your
In the
substrate.
plate, you can see that there is something attached to the plate, something square. Maybe it is not visible properly. We will show you the substrate in a different way.
Okay.
We have a camera inside. We can show you the substrate later. Right now, I will show the transfer, how we transfer. So you can see. I will first take this and move it up.
Yeah.
Now you can see. You see two bolts and we have a notch here. So using those, we can easily.
Once you are locked, can we hold it there for some?
Yes, sure.
Yeah, so that I can move it.
So you can.
Okay, all right. So can you just move it slightly up and down so that it clearly see?
You can see.
Okay, okay. So now we are transferring the substrate from the cradle to the buffer chamber.
So now from the FEL chamber to the buffer
Buffer
chamber,
chamber.
we are transferring the cradle. So you can see now I have transferred my sample.
And now this that we see at the thing is your substrate.
Yeah, we definitely need to close the gate valve because the whole process is like to have the system load lock so that the pressure doesn't, when we increase the pressure here, it doesn't increase here. So, yeah.
I am closing the load lock now. from the buffer chamber by the gate valve, so that the pressure here, which is not as good as the buffer chamber, does not affect it for too long. So we want to minimize this process when the load lock is open to the buffer chamber. So it just took us maybe a minute, and that is only till the time which sees the bad pressure.
So after this, I said it is a storage chamber. So that this is why this is a storage chamber. You can store different samples here, substrates here. Now I said also it is a preparation chamber. So if you come here, so this is a chamber where you can see a manipulator. What is a manipulator? It is a platform where you can keep your plate and you can heat it up properly. You can also move it as you want.
So the flat portion that we see with a hole at the center,
Yes,
that's
yes.
the manipulator.
That is called a manipulator.
Okay.
So now I will say that we have to transfer this into this manipulator.
Okay, so first motion came from Z direction.
Yes.
And now it's in the X direction.
Yes. So this is we call the vertical transfer, what I just did. And now we want to do a horizontal transfer. For that, we have a horizontal hand here, and it is similarly magnetically coupled, as I have said earlier. Now we have to be very careful here because we don't want these hands to bend and collide. So we will slowly do this very carefully. So first we will move this hand.
This is another magnetic movement.
Yes. You can show here that the horizontal arm is moving.
Yeah, okay, so the thing that came in now.
Yes. So you can see, you will.
Yeah.
Now I will actually move this to align the arm so that it is just below our substrate.
So you can selectively
Yes.
take a substrate.
Yes, exactly. So there are different positions and I can take the sample whichever I want. So you can see. Yeah. Yeah. So you can see my arm is just below the
Yes, yes.
level
So
of the.
it's like having a pincer in vacuum.
Exactly. I mean, we have an arm, we are putting it on the arm. So you can see, slowly I will do it so that nothing collides. It is very important. Because if the arm bends, we then again have to open this chamber and again to get the vacuum, we will take 2 minutes.
Any small mistake takes a long time
Yeah.
to correct.
And now, so you can see I have transferred the thing from the vertical arm to the horizontal arm.
Correct, correct.
Now we will take it out again, slowly.
So you are taking it back.
Yes.
And then the vertical arm will go down.
Yes, we need to put the vertical arm down so that if we come again in this direction, it doesn't collide. So now this is, we have transferred our substrate holder from the cradle, vertical cradle to the horizontal arm. Now we want to transfer it from the arm to the manipulator. So for that you can see, we have a remote here and we have a controller here. If you can show it. Sorry. Yeah, so this is a controller which controls the manipulator and we can control it using this remote control.
Okay.
Yeah. So I will set it on the move mode. Now I can move the thing using these buttons in the remote. So I will just take the manipulator down. So all the way. You can see.
So the substrate is?
The substrate is in the horizontal arm.
Yeah.
It is
Okay.
in the back. You cannot see it right now.
So maybe you can also look into the camera.
Yeah,
And move.
I can. So now I will move the horizontal arm just above the manipulator. Yes. Now I have to see
So
that if it is
now the
aligned.
substrate has entered the manipulator stage.
Yeah. Now it will slowly go up, and I can manage the alignment. You can see it has not sit, and now it has. So you can see the substrate horizon. No, it's okay. The camera is okay now. I have seen it. So you can see it is the substrate is actually placed on the manipulator now, and so this is now in the manipulator. We can actually heat it up to get rid of all other impurities. And also, if you can focus here, below you can see a circular thing with a hole in middle, right?
Yeah.
This thing. So this thing is called a hydrogen cracker cell. So this hydrogen cracker cell, what it does is it can spray hydrogen atoms on the surface of your substrate, and it can take out many impurities, as hydrogen atom is very reactive, right? Not the molecule, atom. Atomic hydrogen is very reactive, and it can take out many impurities, especially oxides, oxygen, from the surface of your substrate. So after this, we actually transfer this substrate from here to our main chamber. In our main chamber.
So basically, all these things that you described until now is preparation of
substrate
for the further growth.
Further growth, exactly.
And this typically takes you about a day. If I have to be, if you have to be really quick.
So here we heat it up for some 4-5 hours. After that, we heat it up here overnight. So it takes a day to prepare the
sample. 2 days.
No,
if
yeah.
I count hours, I'll say 2 working days.
Yes, maybe. So after that, we can just put it again in similar way. We will transfer it on the horizontal arm, and we will transfer it in this main chamber. If you can show, we will not do it now because we already have a sample there, substrate there in our main chamber. But yeah, we transfer it from here to there.
So am I focusing at the right place?
Yes, exactly. So maybe Rudra will explain what we do in the main chamber now, and after that I can explain what is happening there.
So Sankadev explained how we transfer our substrate to the main chamber. Now it is transferred to the main chamber and we want to grow. So for example, we want to grow A, B to some kind of material which has A atom with 1 ratio and B atom with 2 ratio. Now, how we control these atomic ratios in our growth? So we measure our atomic flow for the molecular beams in atom per centimeter square per second. Now, I hope you saw like bright thing glowing just below the manipulator. So this is called a beam flux monitor. Oh, no, fine. So this is called a beam flux monitor. Is it fine?
Yes.
Okay.
So you can see that this thing is the beam flux monitor. You can see a glowing thing and the filament above it. Can you see? So you can see a glowing thing and the filament above it. So this is the beam flux monitor, which was glowing explains to you properly. Yeah.
Okay, so now let's explain the working principle of beam flux monitor. So I'll play a video. So this is the hot cathode, which is glowing. So because of the heat, it produces lots of thermionic electrons. And if some molecules comes in between the electrons, then the electrons will knock out the some of the electrons from the atom, and it will make it to a positively charged ion. Now this positively charged ion will be collected in the collector, that will be converted to the collector current. Now by measuring the collector current, we can directly convert that how many atoms are flowing through the beam flux monitor, and through that we can measure the atom per centimeter square per second flux ratio, and we converted from the current from in the collector. So this is the video from the Pfeiffer vacuum showing the exact working principle of how the beam flux monitor works. So here you can see the electrons are emitting and it is ionizing the atoms, and this ionized atom is collected in the collector, which is measured in the collector current. So from that we calculate our collector current. So I'll do a quick demo of the beam flux monitor. So here we have a beam flux monitor software in the PC. Maybe you can come here to show that. So, and here we have our no, but we need just okay. Okay. So now you can see the MB controller. So we can open the we can control the temperatures of the cells from here. And
Wait. Could you explain what this screen is?
okay, so this is the screen to control the effusion cells of the MB. So here
So the effusion cells that Tansadeep showed in the beginning, that there
yes.
are many of them,
Yes.
and you can control them individually through the software here.
Yes, correct. So here I can open one shutter, and maybe you can see here. Here we have opened the beam flux monitor. So this is our software for beam flux monitor. Here we can get the information of the collector current. Now, if I open the shutter, so I have opened it, you can see the collector current has increased. So from that we can calibrate the atom per centimeter square second. So you can see the collector current was here earlier, and it went up to here, and we are measuring the collector current, and we note down this parameter too for our growth for each of the individual flux and calibrate our.
And this would be different for different materials.
Yes, ideally the cross section can be different at ionization cross section, but we have a calibration curve for each material,
Okay.
and from the collector current we can convert to the atom per centimeter square per second flux ratio.
So you always know temporally how much time for every layer also
Correct.
for a given material.
Yes. So now we'll go back to my slide. Yes. So there is another way to calibrate the flux, which is done via quartz crystal microbalance. So the quartz crystal microbalance is a quartz oscillator which oscillates at particular frequency. Now, if you put some mass on it, the frequency decrease. So by checking the frequency, we can find out the how much mass is getting deposited on the QCM. Hence, we can convert the mass to atomic number and get the atom per centimeter square per second ratio of the flux of the this molecular beam effusion cell
So just
from the effusion cell. Yes.
for clarification, so you have crystal resonators
Yes, yes.
whose frequency changes or what changes?
The frequency changes
Frequency changes.
as the mass is
As
getting.
you-
Yes.
as the mass. So it's like, so one says that whatever gets on the substrate also gets on the oscillator.
Yes, so we put our QCM, as you have seen, the beam flux monitor was just below the
Yeah.
substrate. Similarly, we have some flexible bellows. So Sankadeep may show that.
So here, this is flexible bellows. So here we have a,
Which part?
yeah, this thing is a flexible bellow. And we can move it using this thing, rotating this thing.
Okay.
If we rotate it, you can show that this is coming out.
Yeah.
The bellow is expanding, and so the QCM, the monitor will come out. And if we rotate it in this way, it is going in. So in the chamber, if you show that in the chamber, you will see, you can see something in the middle, right?
Yeah.
That is the quartz crystal monitor. Just in the place of BFM, the beam flux monitor you saw, there you see the quartz crystal microbalance, and I can move it, you'll see, using the bellow. I'm moving the bellow, and you can see it is just, yeah. So using this, we can actually position the crystal right below the manipulator. So that is exactly how the quartz crystal microbalance looks like. Rudra will explain.
So basically, this is a very closed loop system, and they are very sure about how much is really grown onto the substrate.
Correct. And the flux ratio.
And also the flux rate.
Correct. So Now we have the number of flux, so we can grow any kind of compounds with particular ratios. But in actually, we are growing some crystals which has some ordered structure. Now, how we can get information about the ordered structure? So to do that, we use electron diffraction. So as you know, electron has both particle and wave-like nature. So we use the electron's wave-like nature to get the diffraction pattern of the crystal. So a crystal has atoms with particular arrangement. So when the electron gets scattered from the crystal, it produces some diffraction spot. So we have a reed gun here which produces a electron beam, and this electron beam gets reflected from the substrate and produce this kind of diffraction spot, which are known as reed spot. Now, with that reed, we can also get other information like how much layer is growing on the sample. So this is a perfect surface, and now as we are growing, we'll directly not reach to second layer. There will be an intermediate step where some chunks are have grown, but others are not grown. So this is a disordered scenario. So because of that, some of the we can monitor the read intensity. So in a perfect surface, the read intensity will be maximum. But as the layer is growing, say 0.25% of the monolayer has grown, the read intensity will drop gradually. And when we get the 50% of the monolayer, so the surface will be maximally disordered and the read intensity will be minimum. And again, when we are the layer is almost near completion, then the read intensity will go up gradually, here, as you can see. And when the next monolayer is perfectly formed, the read intensity will be maximum again. So this is called read oscillation. So using the by focusing at one particular beam and monitoring its intensity, we can get information about the monolayer formation also. So by monitoring the read oscillation, we can get some idea about the growth and growth rates. So let's see a video to clear our understanding of the inside of MB. So these are effusion cells, and as we are heating up the effusion cells, the atoms are getting deposited on the substrate. And using a reed gun here, we are shining an electron beam, and this electron beam is getting reflected from the substrate. And in the substrate, then in the screen, you can see the diffraction pattern. And by looking at the diffraction pattern, we can get lots of information about the crystal and the growth. So now,
So you are able to see the crystal growth live
live,
as it
yes.
progresses.
So we can see the we can monitor the real-time crystal growth and different layers also. So combining all of these methods makes the molecular beam epitaxy possible. So now we'll demonstrate a growth of our thin film live. So we have a gallium antimony substrate, and we have prepared the surface, and surface looks like that, and the corresponding read pattern looks like that. And we'll try to grow YBSB2, which is has this kind of crystal structure, and the surface looks like that, and the corresponding read pattern will looks like that. So we'll try to grow that. So maybe you can reset the few things. Okay. So open the pyrometer. Okay, okay. So now here in the video, we can see the substrate here. No, I'm sharing the screen.
Make it full screen.
Okay. So this is the substrate. So substrate is mounted here and it is rotating. And with the camera, we have a pyrometer in the MB through which we can monitor the substrate temperature and see the substrate. Now we are also simultaneously monitoring the read pattern. So here you can see the reed spots, and
So
as
the
the
green part right now, it's
reed spots, and these bright spots are the reed spots, and as the substrate is rotating, the reed spots are also rotating. Now we'll what we'll do, we'll start our growth. So for doing that, we'll use ytterbium and antimony with particular ratio, and let's open the shutter.
So we have already reached some temperature in this effluxion cells. In this effluxion cells, we already have reached certain temperatures. These are, we already have calibrated the fluxes of these two cells. The LTEX cell you see, it has ytterbium in it. And the TCC reservoir, the TCC cell is a antimony cell. Now we will open both the shutters, but you can see the manipulator shutter. So the manipulator is the place where our substrate is kept. There the shutter is closed. So as the shutter is closed, even if we open this, it will not deposit on the substrate. So right now, we will open these shutters like this. So both the shutters have opened, but it is not yet depositing on it. So when I open this, the deposition will start. Now you can look at the reed pattern and you will see what will happen.
So now I'll just open the manipulator MB shutter.
Maybe show the reed
And yes, we are seeing the reed pattern. And you can see the reed pattern of the gallium antimony. And similarly, like other cells, we'll just open the manipulator shutter. And now we have opened the shutter, and I would like you to closely look at the reed pattern, and it will slowly change. It's fine.
this read pattern.
Ah.
Could you make it slightly bigger?
Okay, yes.
And just for the
Yes,
clarification to the viewers, we are looking at the electron diffraction.
electron
pattern of
diffraction pattern.
What is being grown.
Yes, correct. So now you can see the patterns are changing. Earlier it was very dot-like, and now they are getting hazy and streaky. Now it will slowly transition to the YBSB to reed pattern as shown in the slide. Now you can see the patterns are, have changed. And by monitoring the read, now we can see that the YBSB2 monolayer has already formed, and we are only seeing the YBSB2 read pattern. And so, like by doing that, we'll do that for some time, like say 40 minutes to grow some 20 nanometer pins, and then we will take it out. And this is how we grow our film. Now, say after the growth is done, let me present my slides again. So we measure the property. So in the here you can see in the TE image, we this is the YBSB2 crystal on the gallium antimony substrate. So this is what we are currently growing, and after growing, we have done a artificially engineered material of semiconductor and superconductor hybrid between YBSB2 and gallium antimony. So gallium antimony, if you measure the resistance, as you cool down the temperature, the resistance will go up. This is a signature of semiconductor. And in YBSB2, you will get a zero resistance state as well as a perfect diamagnetism from the superconductivity. So here what we have done, we have combined the semiconductor and superconductor into a single entity. Now these kind of structures can be like also used to look for topological superconductivity and next generation quantum computing, but currently we are not doing that right now. So this we can do beyond this epitaxial growth also, like not just growing on substrate. We can go beyond some substrate, and Shikhar is going to explain that.
So, hi. Hi. My name. Yeah. Hi. My name is Shikhar. So, Rudra alluded to something about beyond epitaxy itself, and let me start with a very obvious fact that when we try to grow these high quality crystalline substrate, we grow it on a hard substrate, and it has a very uncool consequence. The uncool consequence is you can't flex it, you can't bend it. As soon as you try to bend it, it will break. As you can see, this is one of the substrate. This is Al2O3 single crystal. Now, if let's say, for example, here I have grown epitaxial high quality antimony film, and you can see that you can actually bend it. Right. So, and it opens a way towards flexible electronics. So once you have grown this material on the hard substrate, so I have grown this material, you can see that it's a negative of that. It's almost a mirror image. I have exfoliated from that copper substrate, which has graphene on top of it. I'll explain you why we need graphene. But you see, you can't bend this copper substrate. Like, it's quite hard. Like, if I'm trying to bend it, it's unbendable. But this thing is bendable when I have exfoliated it. And once you have exfoliated it, you could actually slap it on your hand, make a device, and
Can we just redo it
Oh.
when my camera is able to capture?
oh yeah.
Yeah.
So
So could you bend it?
yeah.
Okay.
So it's bendable. If you make a device out of it, you can actually slap it on your hand, and maybe, let's say, you can measure the pulses from my hand itself. And it's not just the pulses. I'll share a video. It's just not about pulses. You can also make human interaction more intuitive. You could actually might be able to just control your window by putting some electronics on your hand, and you could just use to control your devices. Or you could use it in healthcare application. You could put the biosensor at various part of your body to maybe see the iron concentration in your body, or to check the pulse rate or not. And or you could use it in computational purposes. So think about it. Once we have grown the sample on a substrate, we kind of don't need the substrate. We were interested in the sample itself. And these samples are 30 nanometer thick. So if you have this 30 nanometer thick sample, and if you make electronics out of it, already have thinned down the limit of what we can do. So if you can actually thin down the electronics that are there in your phone itself to a micron level. So the film that I have showed you here, this film is 30 nanometer thick, and it is on a polymer which is a 30 micron thick polymer. So that's quite a good advantage.
So basically, you grow a material
Huh.
and then you are able to transfer it to some other material.
Yes, but so there are a lot of application to it. But the point is, how do you do it? And thing is, it's not that easy. First of all, you have the substrate. And if you try to grow on the substrate directly, what will happen is it will form a chemical bond. And these are strong covalent ionic bond. So you won't be able to peel it off. So you need to devise a strategy such that this material that you are interested in, you will be able to peel off. But you also want to make sure that it grows in a high quality single crystal manner. So how do you do it? And the answer is using a material that I alluded to, which is graphene. So here is one of the example, a real world example of a single crystal gallium nitride being used to make a sensor to detect pulses in your hands. So yeah, so I was saying, like, how do you do it? And the way to do it is use the monolayer graphene. The advantage of, there are threefold advantage of monolayer graphene. Twofold advantage of monolayer graphene. First of all, you put this monolayer graphene on your substrate. So this graphene has a van der Waals interaction. And due to the van der Waals interaction, if you try to deposit on graphene, you will be able to peel it off. That's first. The second thing is graphene is thin enough so that the substrate that you are seeing, the electric field can pass through graphene. So whatever material that you are depositing, as Rudra told you, through the effusion cell, that material can still feel the lattice underneath it and could grow epitaxially. So graphene helps in two ways. First of all, it provides an interface that could be peeled off. And second of all, it provides epitaxial relationship with the substrate underneath it. Now, so here is one more example where we have exfoliated antiferromagnetic film. And the third thing is you need a monolayer graphene. If you grow a thicker graphene, a time will come that it will completely mask the surface. So you will be able to exfoliate it, but there will be no interaction with the substrate. So the material that you are growing, it will grow in a random fashion that you don't want. You want a high crystalline single crystal membrane. So the point is, then the point becomes, how do you grow single layer graphene? This is like 0.4 nanometer thick. And the answer is we use copper. So what we do is this copper act as a catalyst for decomposition of methane. Methane has CH4. So you want to take those hydrogen atoms away and you just want the carbon. So copper act as a catalyst to decompose this methane. And when the methane decomposes it gets deposited on the copper surface itself. Now, the way to do and the second point, this copper, it first act as a catalytic center. Second of all, there's an epitaxial relationship between graphene and copper. So we are talking about epitaxy. So the thing is, graphene, we can grow graphene in a single crystal manner itself if we grow a single crystal copper. So that will be the first step that Kaushal will show shortly. How do we grow a single crystal copper itself? And on top of it, we grow a single crystal graphene. Then we'll take this copper piece and put it into a CVD, which we call chemical vapor deposition. It's a high temperature technique through which we grow graphene itself. Then what we do is we exfoliate graphene from the copper surface. So here I have an example of exfoliated. Yeah, here I have an example of exfoliated graphene from a copper surface. I think it should be visible.
So
Yeah.
the dark thing.
Yes, dark thing is graphene.
Graphene.
We have grown it's in it's a thicker graphene multi-layer so that it is visible. If it's monolayer, the light absorption is very less, so you won't be able to see it. So it's a thicker graphene, but again, we have a control over how many layers we can grow. And right, and then at the end of the step, we transfer it on the arbitrary substrate. So you could see, is it visible? There is a slight color contrast. If you, yeah. So that darker region is the transferred graphene.
Okay.
Yeah. So that's how we do it. We exfoliate the graphene, we transfer it on an arbitrary substrate. So let's start with the copper growth itself. Yeah. So Kaushal will tell you about the copper growth through sputtering technique. Yeah, Kaushal, you can take over.
Camera on. Kaushal.
So am I audible? Am I audible? Shikhar? Yeah, okay. So yeah, as Shikhar has told you about the copper growth, we need the copper to grow graphene on it. So we are going to grow the copper using the sputtering process. So here you can see this is the sputtering chamber. And inside the sputtering chamber, we will put our sapphire substrate, and on that we will grow the copper. So you must be hearing this sound, where the sound is coming from. So these are our pumps, which are creating a vacuum state of 10⁻⁷. And when we will introduce a sputtering gas in it, the vacuum level will go up. So we are using argon gas as a sputtering gas inside this system. And in this system, the vacuum is 10⁻⁷, unlike the MBE machine that you saw before. because MB is a very precise machine. But in this machine, we use a different kind of process to grow the materials. We use the fourth state of matter, which is plasma, to grow materials in this machine. So how this plasma is created? So you can see there is this thing which is coming out of this sputtering chamber. This is called the sputtering gun, and the sputtering gun is used to create the plasma. So now you can see here is the sputtering gun, and the sputtering gun has the copper target material, which you can see on the top. This copper will go from this target to the substrate when we will apply the voltage. So now I will tell Meet to apply a voltage. You can see behind there is our power supply. So this power supply will. So we have already modulated how much voltage we require and how much time we are going to deposit this film for. So now here I will tell you how this plasma is created. So when we will apply the voltage from behind, you can see here are some wires. So from here we will apply the voltage, and after the voltage applied, here we will have a lot of negative electron particles because of the negative voltage, and that electrons will create a negative field which will throw away all the free electrons inside the system away from this cathode material. The free electrons come from the sputtering gas, which is argon, and then there are magnets behind this copper target. So you can see it's sticking here. There are a lot of magnets behind. So these magnets create a magnetic field which is perpendicular to this copper target. So the magnetic field will be in this side, and the electric field will be the perpendicular to the magnetic field. So this setup will create a trapping of electrons here, and these electrons start moving around a circular or a helical path around this target. And these electrons will collide with the argon ions, which are created because of the movement of electron away from this target material. So these argon ions are positively charged, and they come towards this copper target. And through the collisions, they knock out copper particles from this target material, which goes straight away because of the large mean free path we create with this vacuum conditions. They go straight away and they go deposit on the sapphire substrate. So now here you can see there is a current. So the current means we have achieved a successful plasma. So now I will show you inside through this window. You can actually see there is plasma. So the pink glow that you are seeing inside, the pink glow is the fourth state of matter, that is plasma. So this plasma we will use to deposit the material. Now you can also see the substrate. I'm going to open the shutter now. So just look in the window, and I am opening this shutter. So those two wafers that you see, those are our substrate materials, and now the copper will start depositing on. So now when the copper growth is done, we will take these substrates and we will go to the CVD system where Meet will grow the graphene film on it, and then those graphene films will be used for different purposes that we have told you about. So yeah, that's it. Over to Meet now.
Yeah, were you able to get the feed? Hello.
Right. So as you saw that we as Kaushal was explaining, how do we grow epitaxially copper on the substrate, and the substrate that he was using was nothing but this the substrate that he was using was nothing but this sapphire substrate. Okay, fine. Yeah. So once we have grown this copper, we are gonna put into the CVD. We have made a small video for your demonstration. Yeah, I'll here with the zoom. Right.
Hi, so this is Meet and I'm going to be talking about the graphene that we produce. So we have a CVD system over here for us, and so the chemical vapor deposition system. Particularly, we have a RTA CVD, which is a rapid thermal annealing CVD system. So, if you have a look at the machinery in terms of realizing the graphene growth through this RTA CVD system, it's not that complex, but I'll show you how it looks like. So, this is basically how the gas machinery looks like. This whole, whole mixture of different lines and different components is what helps us control the gas flow. This here is actually for methane. Methane is basically the carbon feedstock gas that we have over here, which will help us deposit carbon or graphene for us on top of the copper. And if you look at this particular component over here, this is to control the gas flow of nitrogen. Nitrogen is an important gas because it helps us to control how good our deposition is happening inside the CVD system with respect to impurities present inside the atmosphere of that particular system. Now, hydrogen is also a gas for us, which we have, which will help us in terms of produce or providing hydrogen, which is lost during the dehydrogenation process at high temperatures during the graphene deposition. So for example, what happens is that this area that we have over here is also something that helps us establish a good amount of control as to how much amount of gas is going inside the CVD chamber or the CVD tube that we have, which we'll show you subsequently. These are mass flow controllers, and mass flow controllers give you a lot of precise control as to how much amount of gas is being thrown into your system itself. Now, if you have a look at our CVD system, this is what it looks like, particularly the furnace part. This is basically the RTA rapid thermal annealing furnace. The heating over here happens through radiation, particularly this is the quartz tube that we use to realize the graphene growth. And I'll right now fire up the system to show you how it really looks like when we do the actual graphene growth itself. Well, a part of it over here. So let's do that. Let's turn up the heat precisely. So as you can see, there is a particular glow, and this is basically heating the furnace over here through radiation. And this is really quite interesting. And from here we can set the temperature and see as to what temperature the system has reached over here. And this particular box over here helps us have a precise control as to how much amount of gas is let in through the mass flow controllers. Well, that was a part of how it looks like with the CVD system. Now we'll be which will show you how the actual samples look like. Thanks.
So, as we see that if we slide the graphene on the substrate itself, it provides an interface that could be peeled off, and that has a both technological and scientific application. In the scientific term, we can do strain engineering, which helps us to actually, when you strain this material, you can change the band structure of the material itself, which changes the property of the material. So you can tailor the material property through straining, or you can also go to the application side where you can make these flexible electronics and put it on your body, or maybe whatever you want to do with it. And so that's what our current status of the lab is. If you have any questions, you can feel free to ask. Thank you.
Yeah. So let me just look at the questions on you.
Yeah.
You want to stop the slides?
Yeah. So, yeah. Okay.
All right. So that was was it from the quantum materials lab. Yeah, so if you
Take few questions.
sure.
Possible to create heterogeneous materials using this technique?
Yeah, I mean, so by heterogeneous, I guess you're meaning that two different kinds of materials, right? Yeah, so the what Rudra showed, basically it is and was an example of heterogeneous epitaxial integration, because should we go back to the slides or close? Oh. Yeah, just yeah, I mean the short answer is yes. Just to give you a little concrete example. So I think so Rudra showed you that in the live demonstration how he grew this material on top of this material, which is gallium antimony. He grew YBSB2 on gallium antimony. So as you can see, even from this image, which is a TEM image, where you are actually seeing the atoms, these are individual atoms, but you can see from the pattern that the crystal structure here is very different from the crystal structure of YBSB2. So you are basically, what he has done in this live demo, actually an example of heterogeneous integration, where you have created a material with a different crystal structure on a material of a different crystal structure. So yeah, so that is routinely done, and that is one of the most powerful feature of this technique.
So this is what makes this technique very unique.
Yes.
And another question is, can one grow blue LEDs using CVD?
Yes. So basically, we generally the blue LEDs people grow by using what is called a MOCVD, like metal organic CVD, which is a little bit different, because you're using a metal organic precursor, but some of the principles are more or less similar. So this is again a chemical vapor deposition technique, whereas here we are using I guess a little less sophisticated technique, which is just a simple chemical vapor deposition, where our precursor, we are using just a methane gas in presence of hydrogen. But in principle, yes, I mean, people routinely grow blue LEDs by this technique of MOCVD.
So I think right now there are no more questions. So if you have more questions about this, please send us an email at outreach@tifr.res.in. We'll relay your questions to the team and get back to you about it. So on this note, let's thank Shovik and team for walking us through the fantastic technique of MBE and the science that they do. And on this note, we stop the session.
Yeah, I hope you enjoyed the live session. Thank you.
Thank you.